Chapter 1, Stress, Application of Normal and Shear Stresses in Design. So in this example, we want to know if we have a concrete block, a cubic concrete block. So this is our concrete block, and we do have a bar, which a part of the bar is embedded inside the concrete. So we want to know what if we are pulling out the a bar out of the concrete block, what is the sufficient length in order to hold it yet inside the bar. So what is the sufficient length, design length of concrete inside the wall, which still holds it yet inside the concrete. We are looking for the sufficient design embedded length inside the concrete wall. So in that case, by assuming that a uniformly distributed of shearing stress, so the tau stresses time the length, so this area in terms of shearing stress, so shearing stress is just tau times PD, mhm, times PD, times L should be equal to force. So in that case, L is just force over tau allowable times PD. mm. Because if you just wide it open, that's the PD. mm, And the length you're working with, for example, this is PD and the other one is L. So that area, if you wide open it, it's just PDL times shear is equal to force. Stress times area is equal to force. So you can easily calculate the sufficient design length. Let's put it into an example. So in this example, a force of P applied as shown to a steel reinforced bar. We have a steel reinforced bar with a diameter of D and in length of L inside the concrete block, which has been embedded in a block of concrete. Determine the smallest design length of L, which the full allowable normal stress in the bar can be developed. We want to express the result definitely in terms of diameter of our rod and normal stress, acceptable or allowable normal stress, sigma, and in a steel, and also average bounding stress between, which is tau, definitely shear between the concrete block when we are pulling out the force between concrete block and yet the steel bar. So that's a bounding stress which applies here. So the first part is just look at the shear area. For shear force, we have a when you start to taking out the embedded part, applying the pulling force in positive x direction to the rod, the embedded part try to prevent from coming out. So for shear part, which applies here, that's the area of shear, which definitely is the definitely that's PD times L. So that's the PD area times length times area, um, two dimensions. So one is PD if you wide it open, and the other one is L. So the total area is PDL, and then force is just shear times the area. So that's tau allowable PDL. And if you recall that equation one, and let's see what else we have. In tension part, we do have the tensional part. The normal force applies to this cross section. So area for tension is just PD squared over 4, a quarter of PD squared, and that's nowhere but just the cross-sectional area which the outward pulling force applies there. That's the greenish area over there, and that's P times D squared over 4. And if we call that, so that's again where normal acts. That's sigma normal times PD squared over 4 equal to P. And if we want to have the fully developed is the condition that the shearing force and normal force are equal to each other. So if we show that by a shearing, equation 1 is equal to equation 2, and both of them, it just says design length is equal to sigma acceptable times a diameter of the rod. So sufficient design length is equal to sigma stress, normal stress, acceptable normal stress times diameter of the rod, steel rod, over 4 times shear acceptable. So that's how we can develop the normal stress and shear stress should be equal to each other to cancel it out. We'll solve more problem on our next video about the same topic.